Welcome to our deep dive into the mathematical, statistical, and algorithmic principles that underpin data science. In this video, we're setting the stage to uncover the fundamental concepts crucial for any data science enthusiast. First, we'll provide an overview of what data science entails, touching on its broad scope and the impact it has on various fields. From business analytics to artificial intelligence, data science is the powerhouse driving innovation. Next, we emphasize the importance of foundational principles. These core elements are not just theoretical, they are the building blocks enabling data transformations, predictions, and decisions. Grasping these basics will empower you to navigate more complex topics with confidence. Throughout this video, we'll delve into mathematics, the backbone of data modeling, essential statistical methods, and key algorithms used for processing and predictions. You'll gain practical knowledge to apply in real-world scenarios. So, let's dive in and unlock the wonders of data science together. Welcome to the foundational segment of our deep dive into data science principles. Today, we explore how mathematics forms the backbone of data science. It's pivotal to understand that without mathematics, data science as we know it would not exist. From linear algebra, where we manipulate and transform data through vectors and matrices, to calculus, which allows us to optimize and fine-tune our models, the principles of mathematics are indispensable. Mathematics isn't just a subject, it's a vital tool. It enables us to uncover patterns, make accurate predictions, and solve real-world problems. Every model, predictive analysis, and data-driven insight stems from a fundamental understanding of these concepts. In the following segments, we will delve deeper into specific areas like linear algebra and calculus, showcasing their applications in data science. For now, remember, mathematics is not just part of data science. It is the essence that powers it. Stay with us as we uncover how mathematics weaves through the fabric of data science, setting the stage for profound insights and discoveries. Linear algebra forms the backbone of data science, acting as a bridge between mathematical theory and practical application. Vectors and matrices are essential tools for manipulating data sets, often representing data points and their relationships. Eigenvalues and eigenvectors play a critical role in dimensionality reduction techniques, which streamline complex data sets for efficient processing. In machine learning, these concepts extend beyond theory into powerful applications. For instance, principal component analysis, PCA, relies on eigenvectors to identify the most significant features in large datasets. Similarly, matrix factorization techniques empower recommendation systems by creating connections based on shared characteristics. As we delve deeper into linear algebra, you'll discover how these mathematical foundations facilitate data manipulation and transformation, enhancing the accuracy and performance of machine learning models. Up next, we'll explore the vibrant world of calculus and its crucial role in optimizing data science models. Stay tuned as we continue our journey through the core principles that drive this fascinating field. Calculus is essential in data science, shaping the optimization techniques that propel data models toward precision and efficiency. Imagine a steep mountain where we aim to find the lowest point. This is where gradient descent, a practical application of calculus, shines. It uses the principles of derivatives to repeatedly take steps downhill, each time calculating the path that will lead to the lowest possible error in our model. This journey is grounded in minimizing loss functions, an essential concept in improving predictive accuracy. Without calculus, optimizing complex data models would be nearly impossible. It provides the mathematical framework for improving algorithms with each iteration. As we proceed, we'll delve into probability theory, another critical tool for understanding uncertainties in data science. Diving into the heart of data science, probability theory is a cornerstone concept. It equips us with the tools to make predictions and understand uncertainties in data. Basic probability concepts lay the foundation for advanced techniques. These include understanding events, likelihood, and random variables. As we progress, Bayesian inference comes into play. This method helps us update the probability of a hypothesis as more evidence becomes available. It's widely used in predictive modeling, enhancing our ability to make informed decisions based on data. Applications of probability theory are vast, underpinning algorithms and models that forecast trends and behaviors. These principles are crucial for tasks like risk assessment and recommendation systems. Grasping these concepts unlocks the potential to interpret and analyze complex datasets more effectively, leading to more accurate and reliable outcomes in projects. In data science, statistical methods are crucial for data analysis. They empower us to condense vast amounts of data into meaningful insights. Descriptive statistics provide tools to summarize data through measures like mean, median, and standard deviation, offering a snapshot of the data's central trends and variability. Inferential statistics allow us to make predictions and generalizations about a population based on sample data. Techniques such as hypothesis testing and regression analysis are pivotal for making informed decisions amidst data uncertainty. Understanding these statistical methods is crucial. Statistics isn't just about numbers, it's about making sense of complex data, uncovering hidden patterns, and deriving actionable insights. As we delve deeper into descriptive and inferential statistics, their significance in data analysis becomes clear. Stay tuned as we navigate through the intricate world of statistical methods and beyond. Descriptive statistics are vital for summarizing and understanding datasets. Measures of central tendency like the mean, median, and mode offer insights into the central point of our data. The mean provides the average, the median gives the middle value, and the mode represents the most frequent occurrence. However, measures of variability, such as range, variance, and standard deviation, inform us about how spread out or clustered our data points are. Data visualization techniques come into play, turning raw numbers into graphical representations that highlight patterns and trends at a glance. Visual tools like histograms and box plots provide immediate insights, helping us interpret data more effectively. By combining these descriptive measures and visualization techniques, we gain a comprehensive summary of the dataset, allowing us to make informed decisions. As we move forward, you'll see how these concepts lay the groundwork for more advanced statistical methods. In this segment, we explore the power of inferential statistics, an essential field for making predictions and inferences about populations based on sample data. Techniques like hypothesis testing and confidence intervals help us assess claims and measure the precision of our estimates. Regression analysis is also crucial for understanding relationships between variables and making data-driven forecasts. By mastering these techniques, we can uncover deeper insights and derive meaningful conclusions from our data. These inferential methods integrate seamlessly with other statistical techniques, offering a robust framework for data analysis. Understanding and applying these principles empower data scientists to make informed, evidence-based decisions. Get ready as we continue to unravel the many layers of complexity and possibility in data science. An algorithm is essentially a step-by-step procedure for solving a problem or performing a task. In data science, algorithms are indispensable. They process data, analyze it, and drive machine learning by transforming raw data into meaningful insights. Algorithms come in many forms, from simple decision trees to complex neural networks. Each type serves a distinct purpose, tailored to the specific needs of a data science challenge. Some algorithms excel at classifying data, while others uncover hidden patterns. Understanding the types of algorithms and their applications gives us powerful tools to make sense of data, predict outcomes, and automate decision-making. The importance of algorithms cannot be overstated. They are the engines behind data-driven discovery and innovation, facilitating everything from predictive analytics to automated processes. As we move forward, you'll see how these algorithms are applied in both supervised and unsupervised learning, revealing their extraordinary capabilities. In data science, supervised learning algorithms are crucial. These algorithms learn from labeled data, making them powerful for prediction and classification tasks. For instance, linear regression predicts outcomes based on input variables, while classification algorithms categorize data. Each algorithm is trained using historical data to recognize patterns and make accurate predictions on new data. Supervised learning is a critical tool in the data scientist's toolkit, driving advancements in numerous fields. As we move forward, you'll see how these principles extend into unsupervised learning, opening new doors to data exploration and pattern discovery. Unsupervised learning algorithms are crucial for finding hidden patterns in unlabeled data. Clustering algorithms group similar data points, revealing natural groupings or categories. For example, in market segmentation, clustering can identify distinct customer groups based on purchasing behavior. Another vital method is dimensionality reduction, which simplifies the data without losing significant information. This is useful for visualizing high-dimensional datasets and improving model efficiency. Understanding these unsupervised learning algorithms empowers us to make sense of vast amounts of unstructured data, uncovering insights that might otherwise remain hidden. As we move forward, you'll see how reinforcement learning enables machines to learn from their environment, paving the way for advanced AI applications. Reinforcement learning is a fascinating field where algorithms learn by interacting with their environment, improving their actions to maximize rewards. Markov decision processes help in decision-making by modeling the environment in states and actions. In reinforcement learning, an agent takes actions, receives feedback, and adjusts accordingly. For example, training a robot to navigate a maze involves learning optimal paths by trial and error. Reinforcement learning has broad applications, from game playing to real-world uses like self-driving cars and dynamic pricing. These algorithms enable systems to make informed decisions, adapt to changes, and improve over time. As we move forward, you'll see how deep learning algorithms build on these concepts to model complex patterns in data, pushing the boundaries of AI. Deep learning algorithms are at the forefront of data science innovation. By leveraging neural networks, they model extremely complex patterns in data. Think of neural networks as intricate webs of interconnected nodes, resembling neurons in the human brain, which process information and learn from it. From detecting objects and images to understanding human language, deep learning algorithms have revolutionized fields such as image recognition and natural language processing. Their applications are vast, from diagnosing diseases from medical images to predicting stock market trends in finance. Understanding how these algorithms function is critical for anyone aiming to excel in data science. As we move forward, you'll see how mathematics, statistics, and algorithms seamlessly integrate to provide powerful insights from data. Stay tuned to dive deeper into the intricate world of data science principles. In data science, the synergy between mathematics, statistics, and algorithms is undeniable. These foundational pillars transform raw data into actionable insights. Mathematics provides the theoretical framework to understand structures and patterns. Statistics allows us to infer and predict with confidence. Algorithms bring these principles to life, solving problems with precision. Real-world applications abound, from predictive maintenance to personalized recommendations. For instance, in healthcare, analyzing patient data to predict outcomes integrates mathematical models, statistical methods, and advanced algorithms seamlessly. The interplay of these disciplines is the heartbeat of data science. They empower us to solve problems, innovate, and drive progress. Stay with us as we delve into specific case studies, showcasing the incredible potential of these combined forces in action. As we conclude our journey through the world of data science, let's reflect on the principles we've explored. We've navigated the pivotal role of mathematics, delving into linear algebra and calculus. We've uncovered the power of statistics in making sense of data. And we've examined the heart of data science, algorithms, each with unique applications and benefits. These building blocks, mathematics, statistics, and algorithms, illustrate the depth essential to mastering data science. They are not just concepts, but tools that empower us to interpret and transform data into actionable insights. As you continue your exploration, remember that these foundational principles are your roadmap. Keep questioning, experimenting, and learning. Thank you for joining us on this journey. Stay curious and let the quest for knowledge guide you further into the fascinating world of data science.